Welcome to a full-length video on the section on vector-valued functions. So this is a really nice piece of calculus because it brings in vectors and functions and a little bit of calculus all together, and it's not that hard, which most people like that idea. So what I'll be talking about today is definitions and graphs. So we'll define what is a vector-valued function. We'll talk about how do you graph a vector-valued function. Then we'll get into the beginnings of calculus. So we'll talk about limits of vector-valued functions. And it turns out that if you remember last year, if you remember how to do first-year calculus limits, doing a limit of a vector-valued function is no big deal. Then we'll get into what you would do next in calculus, and that is continuity. So again, if you remember what it means to be a continuous function, then you should have no problem understanding what it means for a vector-valued function to be continuous, both at a point and in general. Then finally, I'll give you a little application of a vector-valued function, a little fun baseball application. So let's get down to the definition. So let me start out, what is a vector-valued function? So first, just in the words, it must be a function. Hopefully you remember what a function is. So remember, a function is a rule that takes for every element in the domain a unique element of the range. And with vector-valued functions, it's all about what is the range and what is the domain. So in particular, a vector-valued function is a function. Now let's talk about the domain. The domain is R1. That means all numbers. So anything on the real number line, all numbers like 7 or 12 or 8. Often we'll use the letter T for the domain because in physics, T is time, and that's often what the independent variable is going to be. And then the range, you shouldn't be too surprised, seeing that we call this a vector-valued function, is the range will be vectors. And I'm writing vectors in Rn, so it depends on the application you're going to be looking at in terms of what n is. For us in this section, we're going to have two that we'll investigate. We'll look at R2, so those are vectors in the xy plane. And we'll also look at n equals 3, so we'll look at vectors in the xyz space. And depending on what you look at, you get different vectors, and they're both useful. Of course, we live in 3 dimensions, but it's much easier to draw in 2 dimensions, and less work in 2 dimensions. So one of the things is that a vector-valued function is equivalent to parametric equations. And that has to do with the fact, if you remember, parametric equations were functions whose domain was R1, so that's the same, and the range were points in Rn. But for every point in Rn, you get a vector in Rn that starts at the origin and goes to that point. And that's how the equivalence works. So the graph of a vector-valued function is more than just the static picture, but it includes how the graph is drawn. So it's dynamic, just like parametric equations, because they are equivalent. We'll have an example. Okay, what we do is we draw the curve with direction arrows. So again, a vector-valued function's range are a bunch of vectors, but if you only draw the endpoints of those vectors, you get a curve, but then if you think of t as time, then you start at the beginning and end at the end, and that curve is going to be drawn instead of just shown. In general, in 2 dimensions, you write a vector-valued function as we'll often use the letter r to represent the function for a vector-valued function. Sometimes I'll put a little arrow mark to show it's a vector. Sometimes I'll boldface it to show it's a vector. Either way, whatever you'd like to do works. We write r of t, t is the independent variable, is equal to f of ti plus g of tj. You can also use pointy bracket notation if you'd rather. Okay, so f of t is a function, g of t is a function, but you get a vector out of this because there's an I and a j. That's in 2 dimensions. In 3 dimensions, it's very similar. You say that r of t is equal to f of ti plus g of tj plus h of t k, and that's 3 dimensions. So if you had 100 dimensions, it would just be a lot of writing, and you'd definitely use pointy brackets. But I'm only showing you 2 and 3 dimensions today just because too much writing. No more, no harder, just busy work to do more. So now let's look at an example of graphing a vector-valued function. So let's suppose you have the vector-valued function, r of t, is equal to 2t minus 1 times I plus t plus 1 times j. And what we want to do is we want to graph this vector-valued function. So let's just explore a little bit. If t is 0, notice you get negative 1 times I plus 1 times j. And if t is 1, notice you get 2 times 1 minus 1, that's 1, 1i, plus 1 is 2, 2j. So you get I plus 2j. So if we sketch that, we'll notice we have this first vector that is the vector negative I plus j. And the second vector is the vector I plus 2j. So I'm just sketching those two vectors. Notice also that r of t is very linear. We have 2t minus 1, that's a line, t plus 1, it's a line. So we expect this to be linear, and it is. So I have the endpoints of two vectors. I can draw those 2 points and then connect the line between those 2 points. But to show the dynamic aspect of the vector-valued function, I can draw these little red arrows to show I'm going to be moving from left to right, bottom to top, as I draw this graph. So it's more than just the graph shown as a static graph. It's actually a graph that's drawn from left to right, bottom to top. So hopefully this makes sense to you. Let's look at another example that's a little more complicated because it's going to be in 3 dimensions. So let's suppose that r of t is equal to cosine of ti plus sine of tj plus tk. And I want to sketch the graph of this vector-valued function. So the first thing is that if we kind of ignore this k, that would be looking at the shadow of the graph down on the xy plane. And if we do that, we get cosine of ti plus sine of tj. So that means x is cosine of t and y is sine of t, and that's just the unit circle. So we can see that at least the shadow on the xy plane should be the unit circle. But we can't ignore the tk, because as time goes forward, we can see that the z component, or the k component, is moving upwards. So we're going to go around a circle, but we're going to go up as we go around that circle. And it turns out that this picture is very famous and very important, and you have billions and billions of them inside of your body. They are called DNA, because this is a helix. So this is a very, very important 3-dimensional graph. So let me show you the picture of that. So we can see that we get a helix. So that shows that we have a graph that is moving, and I'm drawing arrows to show that we're moving along this helix around the arrows, as we can see. Okay, and it goes on forever, but you can only draw some of it. And that's the graph of r of t is cosine of ti plus sine of tj plus tk. Okay, so now that we have that, let's do a little calculus. So if you remember, the very first thing you ever did in calculus, probably, were limits. Let's talk about how do you define a limit of a vector-valued function. So the good news is the definition is very simple to use and very simple to state. All we can do is say that the limit of a vector-valued function is just the limits of its components. So a vector-valued function is going to have components, 2 if it's an R2, 3 if it's an R3, etc. So you take the limit of each, And you get a vector when you do that because we're plugging in a value of t after, and that will give you a limit. If you don't plug in a value of t, if you just plug in t, you'll end up with a vector valued function for the limit. So in particular, the formal definition, for 2 dimensions at least, is the limit as t goes to some number a of the vector valued function r of t is equal to the limit as t goes to a of f of t, all that times I, plus the limit as t goes to a of g of t, and all that times j. And for 3 dimensions, I bet you can guess, the limit as t goes to a of r of t is the limit as t goes to a of f of t I, plus the limit as t goes to a of g of t j, and then plus the limit as t goes to a of h of t k, where r of t is f of ti plus g of tj plus h of tk. And that's the definition of the limit of a vector valued function. So to find the limit, say in 3 dimensions, it just means you have to find 3 individual limits and then put them together. So let's look at an example. Let's suppose that r of t is equal to sine of 2t over t, I, plus 3e to the t, j, plus t squared minus 1 over t plus 5, k. And let's suppose we want to find the limit as t goes to 0 of r of t. So this is not that hard. It looks messy, but it really isn't too bad. You just got to remember when we're trying to find a limit, we take a limit of each of these independently and then put them together. So let's start out with sine of 2t over t. So the limit as t goes to 0 of sine of 2t over t, if you plug in, you get sine of 0, which is 0, over 0, that's 0 over 0, and that sounds hard, except remember, we have L'Hopital's rule. So I'm going to use L'Hopital's rule, which you can do when you get 0 over 0, and we take the derivative of sine of 2t, use the chain rule, derivative of 2t is 2, and the derivative of the sine function is the cosine function, and you plug in the 2t. So the numerator becomes 2 cosine of 2t. Denominator, derivative of t, is 1. Now we could plug in cosine of 0 is 1, so you get 2 times 1 over 1, which is just 2. So now let's find the limit of the j component, 3e to the t. So here we take the limit as t goes to 0 of 3e to the t, and this is really easy because 3e to the t is just a continuous function, so we can just plug in, and you get 3e to the 0, and that's just 3 times 1, which is just 3. And then similarly, for the third component, the k component, we take the limit as t goes to 0 of negative t squared minus 1 over t plus 5. And again, this is continuous also because the denominator is non-zero. So we get negative 1 over 5 when we plug in 0. And that's just 1/5. So now we could put these 3 pieces of information together to answer the question. We could say the limit as t approaches 0 of the vector valued function r of t is equal to 2i, because our first limit was 2, plus 3j, because our second limit was 3, plus 1/5 k, because the third limit was 1/5. And that's a limit of a vector valued function. Okay, now let's go to the next topic that we do in calculus, and now we're going to do it with vector valued functions, and that's continuity. So it turns out, if you remember the definition of continuity for functions of just a regular old variable, meant that a function was continuous if the limit existed, and when you plugged in, you got something, and what you got was that limit. Well, it turns out it's the same thing. So we could say a vector valued function, r of t, is continuous at a value, t equals a, if r of t has continuous components at t equals a. So as long as each of the components are continuous at t equals a, the vector valued function r of t is continuous. The same result that we had for continuous holds. R of t is continuous at t equals a if the limit as t goes to a of r of t, let's call that L, and let's say L is a number, a defined number, a value. And that should be exactly the same as what you get when you just plug in a to the vector valued function r of t. And if they're the same, then we say the vector valued function is continuous at t equals a. So in general, r of t is continuous if r of t is continuous for all values of t. So if it's continuous for any value you plug in, we call r of t a continuous vector valued function. So let's look at an example. So it says discuss the continuity of r of t equals t over t minus 3I plus the tangent of t, j. So to solve this problem, all we have to do is look at these components individually. And the way we did just regular old functions is we found out when they were not continuous. So let's start with t over t minus 3. That's a fraction. Fractions go bad when the denominator is 0. Well, that means t equals 3. So t equals 3 is bad, not continuous. Now let's go to the j component, the tangent of t. So tangent of t, if you can remember, is the sine of t over the cosine of t. So that means that's going to go bad when the cosine of t is 0. That happens first, at least for positive t, at pi over 2, and then at 3 pi over 2, and 5 pi over 2, and 7 pi over 2, etc. Also at negative pi over 2, and negative 3 pi over 2, all of those. And if you remember from your trig, those happen when t is pi over 2 plus k pi, for k being some integer. So we can say that r of t is continuous for all real numbers, except at t equals 3 and t equals pi over 2 plus k pi. And that is the full story of the continuity of this vector valued function. Okay, now let's look at an example of using vector valued functions. And it's one of my favorites. It's following a baseball. How could you not like following a baseball? So here's the question. Ball is hit along the first base line. But since there is a strong perpendicular wind that's in the direction of the third base line, the position of the ball is r of t is 25t I plus 6t j plus negative 9.8t squared plus 20t plus 0.8 k. So just to give you some reasoning on why this might be an equation of a ball that's hit. So this 9.8, hopefully you've seen that before. That is the acceleration of gravity. By the way, this is in meters and seconds. T is seconds. And the components are in meters, because that's how we do science. This 0.8 means the ball is about 0.8 meters from the ground when the player hits it. And the 6t, that is the wind pushing it towards the third baseline. The 25t and the 20t here and here, the I and k components, that's the initial velocity that happens. Again, we'll get into that in another section, but for now I'd like to give you little hints on what's coming up. So the question is, where will the ball hit the ground? So to answer this question, the key is you have to think about what is the ground. The ground happens when the k component is 0. That's where the ground is. We set the k component to be 0. Negative 9.8 t squared plus 20t plus 0.8 equals 0. And if you really want to torture yourself, you can use the quadratic formula. You could use a calculator, you could use a computer, but hopefully you know how to solve this. And you get two answers. One of the answers gives a negative value for t, and that doesn't work because the ball hadn't been hit yet at a negative value of t. So you take the positive value for the positive root, And I got my calculator about t equals 2.08. And again, that's in seconds. So the question is, where will the ball hit the ground? So what we do now is we plug in 2.08 for t for each of these. And again, I use my calculator. And if I plug in 25 times 2.08, I got 52. If I plug in 6 times 2.08, I got 12.48. And we know that if you plug in 2.08 for the k component, you get approximately 0. So what we can say is that this baseball will be at the position vector 52i plus 12.48j when the ball hits the ground. And that is the end of this video. I hope you understood what a vector valued function is, how to find the limit of a vector valued function, how to find out if a vector valued function is continuous at a value of t, or just if a vector valued function is continuous in general. And we got to play around with baseball. So if you have any questions, please let me know, or if you have another instructor, please talk to your other instructor, and I'm sure that instructor will be happy to help out. So until next time, have a wonderful morning, night, day, evening, weekend, whenever it is for you. So take care.